So today we learned about equilibrium of rigid body. Yesterday we have learned how to calculate a moment, right? A couple moment. And last time we studied about the force that act on rigid body. So what is a rigid body? It is defined as a body which doesn't deform under an influence forces. So when a rigid body is subject to an external force, the internal force is occur as an interaction between particles, like particle A and particle B, inside the body. So these internal force are interact between particles within the body with equal force, equal amount of force, but in opposite direction. And of course, they must share the same line of action. And this causes the property of transmissibility. Like when you exert the force on the left hand side, it will transfer to the right hand side with the same amount and the same direction. So this is the explanation for sliding vector. The vector can slide from one point to another point if they share the same line of action. Okay, so for the rigid body, we must use this fundamental. And for studying the equilibrium of rigid body, we need 2 out of 3, Newton's law of motion. Okay, so here, principle of transmissibility. Like last time that I explained, that assume that we exert force, a pair of force F and minus F. With these two force, have the summation force equal to 0. Therefore, although you exert this pair of force, it will not affect the overall system. And minus F and F on left-hand side and right-hand side will cancel each other. So it seems like we can slide or move this force to another line, another dot, another place on this line. That's principle of transmissibility. Now the first law of Newton. To study equilibrium, we need 2 laws. The first law, that the particle originally at rest or moving in a straight line with constant velocity, it will remain in this state until it is subject to an unbalanced forces. Or it can be expressed as equation sigma F equal to 0. But for statics, we need to consider 2 conditions. Not only sigma F equal to 0, the object must stay at its place, so sigma v of velocity must be equal to 0 too. Or it is the object is not moving. Okay, stay at its place. So we have both sigma F equal to ma, sigma a equal to 0, and sigma v equal to 0. And the next law that we're going to use on this class is the third law. It said that if body A exerts a force on body B, then body B exerts a force on body A. And these two forces have the same magnitude but are opposite in direction and act on different bodies. So this law is known as action and reaction force. Like the force that act on body B have the same amount but in opposite direction with the force of body B act on body A. And sometimes these two forces can be considered as internal force. Okay, and in static, the external force is not included. I will explain later. So in this chapter, we will study how to apply the method of the force system to determine the equilibrium of rigid body. So normally, when we have a force that apply on the rigid body, okay, we have one rigid body and then apply a force in this direction. So this force will cause the movement on this rigid body, but not only the movement, it also cause the translation. The rotation. So for rigid body, if you exert a force, it has both translation and rotation. So we need to consider both F, sigma F, or the resultant force, Fr, together with the resultant moment, Mr, about any point. So for a system that contains forces and couple moments, as shown in this figure, we can reduce this system of forces and couple moments to be an equivalent resultant force and resultant couple moment at any point. In this figure, we use point O. So this point or rotation point can be located inside or sometimes outside the body. And if the resultant force and couple moment are both equal to 0, then the body is considered to be in equilibrium. So it must satisfy these two conditions, F equal to 0 and moment about any point equal to 0 too. So in this first part, let's start with equilibrium in 2 dimensions. So in 2 dimensions, the system will locate in the XY plane, only in XY plane. And any couple moment, okay, so we have XY axis. And the force contained on this space, when the force acts to rigid body, we need to find the distance from point O to the line of action of this force equal to D. So we have one force and one moment. If the force lies on the XY plane, anywhere it placed, the moment will direct along the Z-axis, or the axis is perpendicular to XY plane, which can be directed to the positive axis or negative axis. It depends on the direction of the force. Then the direction of the moment is only clockwise or counterclockwise. Okay, and about Z-axis. When the force system lies on the XY plane, for example, this one, the force can be resolved into X and Y components. That's why we have only two terms, right? F equal to Fxi plus Fyj. Only the force in direction of X and Y. So in equilibrium, the conditions of equilibrium in 2D system, we have to satisfy that the sum of each component must be equal to 0. And again, because it is a rigid body, when we exert a force, the moment will produce. That the moment must be equal to 0. So we have 3 equations to satisfy for scalar. Okay, sigma fx equals 0, sigma fy equals 0, and the moment about any point equal to 0 too. Although you change the point from point O to, for example, to point R, the moment still remain the same. So no moment is produced in the system. Okay, so here are the basics. But sometimes in equilibrium system, we need to satisfy all these conditions, right? But how can we state all force? Or how can we know that how much force that act on this body? The best way to analyze the system is to draw the free body diagram. So the procedure for drawing a free body diagram. First, let's decide which body to analyze, and then free that body from its surrounding and draw the outline shape. For example, in figure A, we want to consider this slider. So let's assume this body a rigid body. Okay, make it smaller. Or make it as a point. And next, we have to show all applied forces on this body, including reaction force that you cannot see. Like for this one, we see only the force P that pulling this slider, but in reality, it still has the weight and, of course, the reaction force between this slider and the floor. So we have N and W act on this direction up and down. And then we identify each force on magnitude and both direction. Any force that acts on the direction of angle can be resolved into its component x and y. So if you resolve it, it will become easier, right? Because you can get the pair of x and y. Now, in most systems, a rigid body is always attached with support to maintain equilibrium. So before we can draw a free body diagram of any system, first we have to consider the reaction of support with two general rules, which are the first one. If a support prevents the translation of a body in a given direction, then the force is developed on the body in that direction. For example, this system. This beam is supported by a roller on the floor. So we all know that this this beam has its weight, W. And this weight will pull down to the floor by the gravity force. So this beam tends to move downward. It tends to move on this direction. Therefore, this roller will support this weight. Then its reaction force must resist this weight. That it must act on the opposite direction. So the reaction force that this roller act on this beam will point upward. Okay, so here is the reaction force that this support act on the body. And okay, this is with this weight too. So first we have to consider if object is placed on any system, in which direction that this object tend to move. Okay, for example, we put this beam on the wall. Okay, and let it support with a weight. So normally, this beam is tend to slide to the floor, right? Slide along this wall. So the reaction force that it should support this beam and make it stay in equilibrium must act on the different direction. Okay, so first, let's see what the tendency of movement in which direction, and the force or the reaction force will act on the different direction. So this, the first rule is will elicit the tendency of translation. For the rotation, if rotation is prevented, a couple moment is exerted on the body. For example, this fixed support. Again, this beam must have the weight, right? And this weight act on the centroid or the center of this body. And if you see the direction between the rotation point and the point of the force, it has one dimension d. That is will cause one moment from this force Mw. The moment that produced with from this weight will act in direction of clockwise. So this wall must prevent the rotation by produce one couple moment to resist it. So the couple moment that this wall produce act on the different direction, which is clockwise direction. And for translation, this beam acting on exerting by this weight is tend to move downward. So the force, we have one force Fy to resist it. And for Fx, again, it has to exert the reaction force to resist the movement of this beam. Okay, the direction of Fx and Fy can be changed if the calculation is changed. So it depends on this condition, sigma Fx, sigma Fy. If after you calculate, the Fx become negative, therefore it means that the Fx that this support actually act to the body, act on the different direction. So first just suppose that the force act on any direction and see the result. Then you can see which direction that this support exert to the body. Okay, so let's see the example of support that you always face in 2D dimension system. First, the cable. So force prevent the translation on this tension. For the cable, it only can exert the force that is pull, right? Pull. Because if you push or act on this direction, the load will lose and it will lose their tension. So the force that you have to exert for this beam must act on this direction, right? To make the load has tension. So these laws must prevent the translation on this direction. So we have the reaction force of tension, T. The tension must act along the line. And also the direction of tensions must act out of the body. So it will always act away from the member in the direction of the cable. Okay, only one direction. So for the free body diagram, okay, we have these figures. The next one is a wasted link. Suppose that this link mechanically is weight or weightless. So the reaction force of the link can be both push or pull. It depends on the system. So for the free body diagram, we have to free this cable from the support. We have one unknown force that the reaction force must act along the axis of the link. As we said that it can be push or pull, so the direction of this force can be direct to the link or direct out of the link. The angle between the force and the horizontal reference is theta. Okay, so for the two supports that I just explained, why is exert only the reaction force, but is not produce the couple moment? So you can see that this law can prevent only the translation, but it cannot prevent the rotation. This beam still can rotate freely. So this support did not create the couple moment to resist the movement, the rotation movement. The same as the weighted link. You can see that on this pin, this slot still can rotate freely. So this support doesn't produce any couple moment to resist the rotation. For the roller too, right? Because this slot is pinned by this pin. So you can see that this slot still move, still rotate on any direction. So this roller does not produce the couple moment, but just only the force. For the roller, we have one unknown reaction force that acts perpendicular to the surface at the point of contact. Okay, so for the free body diagram, we have one force that must act perpendicular to the contact surface. And the direction always acts to the body, because if this rod has a weight, W, and after that, you resolve this weight to its component, okay, along the axis along this rod and perpendicular to this rod. It is W parallel and W perpendicular. So you can see that this support must resist this force. Therefore, it must act on the different direction or act to the contact surface and direct to the body. The next one is the locker. Actually, it looks like the roller, right? But roller has support by the wheel, but the locker support by the curved surface. But if you observe the contact surface between the floor and the locker, it will touch the floor at the tangent point. It's just a small area. So we use the same fundamental as the roller. That is, the reaction force that the locker acts on this body must be perpendicular to the floor or the contact surface, and it will point up to the object. Okay, always on this direction. The support number 5 is like number 3 and 4. So you can see that on the curved surface of this slot, the contact surface between the floor and the object is just a small area. So the free body diagram is like support number 4. That the reaction force must act to the contact surface and perpendicular to the floor. Always act to the body. Here on this object, these figures, the force must be act perpendicular to the floor, right? So the contact surface, the contact force, the reaction force act on this direction. Case support number 4 and number 5 is the same, is that it cannot prevent the rotation. So no couple moment reaction is produced. The support number 6, it is the wheel that placed between two floors. Or this wheel is clamped by this floor. For this type of support, we have one unknown reaction, the force that acts perpendicular to the slot. But the direction can be possible in both directions. It can be point to the body, or it can point out of the body. It depends on the final value when you calculate the equation, that it is positive or negative. Okay, and must act perpendicular to the floor. Okay, because it can resist only the translation of this slot to the left or to the right, but it cannot prevent the rotation. Support number 7 is a member pin connected to collar on smooth slot. So this pin, this slot is pinned with this collar, so it still can rotate on clockwise or counterclockwise direction. So it can prevent only the translation. We have only the reaction force. On this type of support, we have one unknown reaction force. And of course, it must act perpendicular to the contact surface. So it's like the support number 6, that the direction of force can be direct to or direct out of the lot. For the next one is smooth pin on or hinge. Again, so you can see that on this pin, this slot still moves in rotation. Okay, so it can prevent only the translation, but the translation can be along X or Y axis. So it has to reaction force along its component. In free body diagram of this type of support, we have Fy and Fx. All these two forces, Fy and Fx, can be find the resultant into one force, Fr. Okay, where Fr equal to Fx plus Fy by vector addition. And this resultant force will act on the floor with one angle. Let's see phi. The angle of resultant force, the angle that and the angle that this lot act on the reference horizontal axis don't need to be equal. Okay, it depends the amount of force, depend on the amount of force, Fx and Fy. Okay, only the resultant force because it's still can rotate. The support number 9 is member fixed connect to collar on smooth lot. It is different from the support number 7. The support number 7 is fixed by the pin, so it still can rotate. But for the support number 9, this point is fixed. It's a solid body. Therefore, it cannot rotate. It means that this type of support must prevent a couple moment to resist the rotation. If this lot is placed like these figures, the tent of rotations should be on this direction, right? Because of the wedge. The possible rotation acts on this direction. In order to resist this possible rotation, the supports must create one couple moment, act on a different direction. So these supports produce this M. And of course, these supports can prevent the translation too. It can prevent the translation along this lot and also can prevent the rotation. So we have both couple moment and one reaction force act to this lot. So we can write the free body diagram and show two things, right? First, the force act perpendicular to the contact surface and one couple moment, M. The last support is the fixed support. So this type of support fixes itself to the place, so it can prevent both translation and rotation. So if this this lot has one weight, the possible rotations is in clockwise direction. Then the supports must create one couple moment to resist this rotation. That is in counterclockwise direction. And for the translation, if the weight of this lot, right, the weight of this lot must direct to the floor or the earth by the gravity. So it must exert one force to resist this weight. That the force must point up, or Fy. For the force in x-axis, so you can say that this lot is tend to translate on this direction. No, sorry, it tend to move on this direction. So we have one Fx, this is the translation in x-axis, point out of the body, Fx. Then for free body diagram of this support, we have one couple moment. And the force that act both on Fy and Fx. And this Fy and Fx can be added into the resultant force. That have the angle between the reference horizontal axis as phi and couple moment m. Okay, so not only the force that you see that exert to that body, but you have to know the reaction force and reaction couple moment that produce from that support too, and then state all forces into the system and find the answer. So here are some examples of actual supports that you always see in your life. Like for example, number one, it is a cable exert a force or the bracket in the direction of cable, right, to support the weight. So the tension will act out of the body every time. Tension. Or this one, it is a locker. The locker supports for this bridge grinder. So for the curved chest, it allows this bit to move to the left or to the right. Right, flexible movement. So the bit can be free to expand or contract due to the change of temperature. Okay, so you can see that it contact surface, it's just a small area. Then the reaction force acts up to the body and also perpendicular to the floor. For support number 10, you can see that it is a fixed support, right? Every junction is fixed by its place. So this type of support is very strong because it can prevent both translation and rotation. For example, the floor beams on the building. So it's built together by fixed connection. So it's made the floor become more stable and more stronger. Okay, the support number 4 and support number 8 is quite flexible, right? Because it still can rotate about any point. On this support number 5, and this concrete guiders lays on the ledge that is assumed to act on the smooth surface. Okay, so in this class, we will assume that all support have a smooth surface in order to get rid of the friction. So it's considered as no friction at all. Okay, so here are some examples of support in 2 dimensions. Besides the reaction force of the support, the other thing that we should consider before represent the system with the free body diagram are 2 things. First, the internal force, and second, the weight and center of gravity. Normally, the internal force that act between particles in the bodies always occur in collinear pair. Like the force that body A act on body B, and the force that body B act on body A. You can see that these 2 pair of force have equal magnitude, but in opposite direction. So you can see that these 2 forces can cancel each other. Is F and minus F. We have the resultant force F equal to 0. Therefore, these 2 forces cancel each other, and they assume that there's no external effects created in the body. Therefore, for the free body diagram in 2 dimensions, we will consider only the external force because we assume that all the internal force cancel each other already. Okay, so the internal force is not included. Next is the weight and the centroid of the body. The weight W on the object is located on the body geometric center or the centroid of the body. So it's assumed that the point happened in the middle of the body. So why? Why do we have to make it like this? We will study on another chapter about the centroid and CG. But the dimension affect the moment, right? Because the weight that act on this point and the weight that act on this point produce a different moment. So we have to locate the light centroid to state the weight of the object. Okay, but for every rigid body, we cannot neglect the weight. Every object must consider the weight too. Okay, so here the importance of the free body diagram. And when you represent the system with free body diagram, you have to idealize the models. Like to perform a force analysis on the object, you must replace the system with the figures that represent everything that you see as closely to the real life situation as possible. For example, this beam support. For this beam support, you can see that it is a 3 dimension, right? But you can also represent this system with 2 dimension figure because the width or the depth of the object is not related to the system. Then we can represent with 2 dimensions because we can only the force and the dimension of the beam. Okay, the depth of the system is not concerned. So we have this free body diagram. Now let's see some example of free body diagram. Okay, the first one, 2 smooth pipe placing on these forks. Okay, let's say that we have 2 pipe A and pipe B. Each pipe have dimensions that are equal. And again, we will assume that all surfaces are smooth. So there no friction occur on this system. On this system, the body that we want to consider is only 2 pipes, A and B. So we just represent with the simple figures. We cut only the force and 2 pipes. Then now we have to consider each pipe. Let's start with A. Starting from object A, we have to free body A from its surrounding, free it from the force and free it from body B, and see how many forces that exert to this body. Of course, we have the weight of A, WA, right? That's the weight always act to the horizontal minus axis because due to the gravity effect. And between the contact surface, the floor and the wall of the force can prevent the translation, right? Because the weight act on this direction. If you resolve is in order to make it parallel and perpendicular to the force, you can see the tenth of translation. Then you can guess the reaction force. That the reaction between this side and the pipe will act on this direction. Let's say F1. Okay, we resolve the WA to this direction and this direction. On this direction, again, the flow of this force must produce one force to resist this weight. So we have another reaction force on this direction, F2. So the pipe A also contact with the surface B. Between the contact surface, of course, we have reaction force, KFB. So here are the forces that act on body A. Now let's see body B. For body B, we have two contact surface, right, between B and floor and B and A. Body B itself produce one weight. And the action force between contact surface A and B have FA. So when you resolve this weight to along this axis, case also have one reaction force from the floor, F3. So now we have to include these two systems together. Okay, you can see that FB that act on A and FA that act on B is on the different direction, but the same amount. So these two forces can cancel each other and can be considered as internal force. So we don't have to care about it. Then we have F1, WA, F2, F3, and WB. Only these 5 forces left with no couple moment because it cannot prevent the rotation. Okay, another example is the food level shown on this system. So let's simplify this system by drawing the figures as shown in the right-hand side. So you can see that the driver exerts the force perpendicular to the pendulum at this direction. And this link is locked by support A and with the spring and one link. So these three supports must create the reaction force to prevent this short link to move. Okay, so for this pin, because it can resist only the translation, but not resist the rotation. So we have only reaction force, AY and AX. Okay, first just suppose that AX and AY acts on any direction. And after calculation, let's see the result that it is negative or positive. If it is negative, it means that the direction of AX and AY will opposite to the first direction that you suppose. Okay, so I will suppose that AX and AY act on this direction first. For the spring, okay, so you can see that if the force exerted on this direction, this side of the link tend to move to the left-hand side, right? Therefore, the spring must prevent the rotation, must prevent the movement by exert the force on this direction, Fs. That is equal to Ks. And for this link, when the force exerts, the link is tend to move to the left-hand side. So the resistance force act to the right-hand side, Fb. The direction of the Fb must act along this link. Okay, so we have 4 reaction force. Okay, sometimes the problems is giving to you as a 3-dimension figures, but you can realize or replace it with the 2 dimensions. For example, this one, if you take a good look, it's like these figures can symmetry, right? This figure is symmetry along any plane. Or in this word, it is a plane that parallel to the lobe. Okay, so we can replace this system with the 2-dimension figure. Okay, or we consider only one side of the system. So this object is holding by a lobe and a link. The object itself produces the weight at the centroid of the body. The tensions always act out of the body, so in this direction, T. And for the link, this type of support will produce the force AX and AY. So just suppose that is act on this direction. Okay, so here are just the example of the free body diagram of each system. Now let's see one example. Okay, for these questions, they want you to determine the torque or the moment applied to the both and the force to the range of the both. So when you exert the force from both hands equal to 52 and 30 Newton to this bolt, okay, it said that the range does not turn. It means that we're still in the static system. So this bolt is prevent the rotation. Okay, so for these questions, we assume that this lot or this range is rangeless, no range produced. So we have only two force exerted on the body. And then the force that produced by this support. Okay, we know that